Our our topic today will be okay. Let's start our class. I will not take too much time. We're going to discuss today the orbital laws of motion, orbital motion laws, you can call it. So we'll discuss three things. First, we'll discuss what are the forces on the satellites. Well, as you know, satellites orbiting the Earth. So what type of forces are there on the satellite? That's our first topic. Second topic will be Kepler's law. Uh, very important laws we'll discuss today. Kepler first law, Kepler second law, and Kepler third law. And finally, we'll see orbital parameters. So topics we are going to discuss today will be forces on the satellite, Kepler's law, and orbital parameters. They are part of chapter 2. So we'll complete chapter 2 today. So let's start from the forces on satellites. So as you know, satellites are orbiting the Earth. Here we have a satellite orbiting the Earth. So in this case, in this case, okay, so let's, this is Earth. With mass ME. This is mass of the Earth. And here we have a satellite with, let's say, mass of the satellite MS. And the distance between the Earth and the satellite is, let's say, R. Okay, so this satellite is orbiting, rotating around the Earth with orbit with a distance R from the Earth. So as you can see on the slide, there are two main forces on the satellite. The first force is force towards the Earth. We call it gravitational force. There is a gravitational pull from the Earth. Okay, we call it Fn. In this case, will be the input force. We call it gravitational force, Fg, which is given by what? Given by, as you know from your physics, gravitational force. G is a constant, gravitational constant, mass of the Earth times mass of mass of the Earth times mass of the satellite divided by R the power of square, right? You know this gravitational force. If there are two objects with mass ME and MS, there is a gravitational attraction between the two. So this gravitational force, which pulls the satellite towards the Earth, in this case Fn is given by this gravitational force, which is equal to gravitational constant, mass of the Earth, mass of satellite divided by R squared. What is the other force? Centrifugal force, F out, as you can see here. Whenever an object rotates around a curve or a circle, there is a force, what we call it centrifugal force, right? This satellite is rotating around the Earth, so there is a force in opposite direction, F out. We call this force centrifugal force. So uh, okay, so F out. Can you hear me? Can you hear me?
Yeah.
Okay, can you see the slides?
Yeah.
Okay, so let's continue.
Okay.
So as I said, today we are discussing forces on a satellite. So as you can see here, when this satellite rotates around the Earth, there are two forces. One force inward, another force in opposite direction. This force is called gravitational force, and this force is called centrifugal force. So the gravitational force is given by this equation. Fg is equal to g times mass of the Earth times mass of the satellite divided by r square. How about the centrifugal force? Centrifugal force, F, let's say centrifugal force Fc, which is given by equation mass of the satellite, right? Speed, because the satellite is rotating with a tangential speed v square, okay, v square divided by r. So this is the centrifugal force which pulls the satellite away from the Earth. So we have how many forces applied on the satellite here? Two forces. One gravitational force towards the Earth, one centrifugal force to, away from the Earth, opposite direction. Two forces are applied on the satellite. When the satellite rotates around the Earth in any orbit, there are two forces opposing each other. One force due to gravity of the Earth, another force, centrifugal force. Centrifugal force depends on the speed, as you can see here. The satellite is moving with a speed of v, so that's what we call it centrifugal force, and there is gravitational force in opposite direction. So what will happen for a satellite to stay in the orbit? These two forces must be balanced out. These forces must be equal. If one of the forces is greater than the other, the satellite will be out of orbit, right? If these two forces are exactly equal, then the satellite will stay in the orbit and rotate in that particular orbit around the Earth. That is the condition. So what's the condition? For a satellite to stay in the orbit, the gravitational force must be equal to the centrifugal force, Fc. These two forces, uh, must be equal. F out and F in, the gravitational force and centrifugal force must be matched, must be balanced. In that case, that's only case the satellite stay in the orbit. So what is Fg? Fg, as you know from this equation, is g, constant, gravitational constant, mass of the Earth times mass of the satellite divided by r square. right? This is gravitational force must be equal to the centrifugal force. Centrifugal force, as you know, if you drive a car around a curve, there is a force to push the car out of the road, right? When you drive in a curve, there is always a centrifugal force. That is depends on mass and velocity. So which is mass of satellite times speed square divided by R. This is the centrifugal force. So here you can see 1R get cancelled by 1R. R is the distance between satellite and Earth. MS get cancelled. So what remains? What remains? V square is equal to V square, the speed of the satellite. V square is equal to G times G, it's a gravitational constant, times mass of Earth, right? Because mass of satellite get cancelled, divided by what? Divided by, here one of the R is get cancelled, so we have only one R. So what will be V? V will be the square root of, because this is square, G times ME, we call it Kepler's constant, we call it mu, is a constant, G is a constant, gravitational constant, mass of the Earth. So what will be V? G square root of G times mass of the Earth divided by R. So what do you understand from this equation? For a satellite to stay in the orbit, the speed of the satellite must be the square root of G times ME divided by R. So you can see here speed is inversely proportional with radius. The radius, not radius, the distance between the satellite and the Earth is R. So R increases, speed will decrease. When R decreases, speed of the satellite must increase. The speed of the satellite depends on the distance from the Earth. So satellites which are very close to the Earth, they are rotating very fast, right? As R decreases, V increases. V is the speed of the satellite. V is the speed of the satellite. So it's inversely proportional. So speed is inversely proportional with square root of R. Okay, this is because this is a constant. So here you see when satellites which are very far, like satellites in geostationary orbit, they are rotating in low speed. When satellites very close to the Earth, like LEO, low Earth orbit, 500 kilometers from the Earth, because R is very small, V will be, these satellites rotate very fast around the Earth. Why this? To stay in the orbit, as I said, for a satellite to stay in the orbit, these two forces must be equal to each other, Fg and Fc. Now, what will happen if you slow the speed? If you slow the speed, the satellite will lose its orbit. So the speed must be equal to radical or square root of G times ME divided by R. It depends on the distance from the Earth. You have to adjust the speed of the satellite. The speed of satellite depends on the distance from the Earth. When you close to the Earth, the speed increases. When you go away from the Earth, the speed must be slow. That way, the satellites will stay in the orbit. So here, as you can see in the slide, velocity required to maintain a satellite in the orbit with radius r is equal to, as I said, mu is g times mass of the Earth. We call it Kepler's constant, this constant, under square root. So v speed is inversely proportional with the square root of r. R is the radius or the distance, the radius of the orbit or distance of satellite from the Earth. Okay. Now, let's go to our, before that, if you have any question, you can ask about the forces. Any question? Okay. So, okay. So let's continue our discussion on next point, Kepler's laws. These are very important laws in satellite communication. We'll discuss 3 laws: Kepler first law, Kepler second law, and Kepler third law. But before that, let me revise what I said before. Okay, so we have Earth with mass of Earth ME and mass of satellite MS. So we need this satellite to rotate around the Earth with orbit with the speed of v. So for this, there are 2 types of forces applied on this satellite. One force is gravitational pull. We call it Fg, gravitational force. The other one is outward, which is the centrifugal force. Okay, so 2 forces applied on the satellite. So what this satellite to stay in the orbit, these 2 forces must be balanced out, must be equal. If Fg, the gravitational pull, greater than Fc, the centrifugal force, what will happen? The satellite will come to the Earth. It will not stay in the orbit, right? Because more gravitational pull from the Earth. If Fc is the centrifugal force greater than Fg, what will happen? The satellite will go to another orbit. It changes orbit. So for this satellite to stay in the orbit, what is the condition? The condition will be these 2 forces must be equal. Fg must be equal to Fc. This is a condition for the satellite to stay in the orbit. So as I said, what is Fg? Fg is gravitational constant, G, you know this from Newton's law of motions, multiplied by the 2 masses. If there are 2 objects with mass m1 and mass m2 with a distance separated by r, there is a gravitational force between these 2 objects. That gravitational force is given by what? From your high school physics, G, gravitational constant, mass 1 times mass 2 divided by what? Divided by r squared, the distance, always there. So similarly here, we have mass of Earth times mass of satellite divided by r squared is our gravitational force, must be equal to the centrifugal force. Centrifugal force is equal to mass times speed squared divided by distance r. So r get cancelled, ms get cancelled, we calculate v. The speed of a satellite must be equal to square root of g me divided by r. So as you can see from here, v speed is related to what? related to the radius of the orbit. It depends on the distance of the satellite from the Earth. If R decreases, there must be more speed. Otherwise, the satellite will fall to the Earth. If the satellite far away, we have to slow it down. The speed must decrease. Okay, that's the first point I want to discuss with you today. Okay, so next let's see Kepler's laws. So let's start from Kepler's first law. What Kepler's first law states that the path or the orbit followed by a satellite, as you can see here, around the Earth is elliptical. As you can see here, this path of the satellite followed is elliptical. Here you see it says elliptical. It's not mostly you think it is circular, right? The path followed around the Earth most of the time we consider circular like this, but it's not circular. The path followed by a satellite is elliptical orbits. Okay, and as you know, ellipse has two focal points. If it is circle, we have only one center. If it is ellipse, there are two focal points. One focal point here, another focal point here from your geometry class, right? So as you can see here, where is the Earth? The Earth is positioned at one of the focal points, one of the foci. So that's the first law of Kepler. Always a satellite path or orbit is elliptical, and where is the position of the Earth? The Earth's position will be at one of the two foci. Okay, because the ellipse has two focal points, Earth is positioned at one of the focus point, so the satellite follows this elliptical path. That is first law of Kepler. Kepler is very famous astronomer in 16th century. So he formulated these laws for planetary motion, but they are exactly works for satellite orbits also. Okay, so first law of Kepler: the path followed by a satellite is elliptical, and the Earth is positioned at one of the two foci of the ellipse. That is the first law of Kepler, Kepler's first law. Okay, Kepler's second law. It's very important to understand this also. As you can see here, satellite position at this point, if satellite is here, and if satellite is positioned here, so the distance from the Earth, in the first case, is R1. The second case is R2. So as you can see here, because it is elliptical, at some point the satellite is very near to the Earth. Here at this point P1, the satellite is at the distance only R1, very close to the Earth. When satellite goes around the orbit and goes to point P2, the distance is R2, which is very far compared with R1. So what we have said, the speed is inversely proportional with what? Inversely proportional with R. The distance and the speed are inversely proportional. So when satellite is at position P1, what will be the speed? Because R is very small, the speed will be very high. So the speed of this satellite, when it is at position P1, is very high speed. When the satellite goes far away from the Earth, and when it's very far, at example at point P2, it's very far distance. So when R increases, what will happen to the speed? The speed will decrease, right? So the satellite rotating around the Earth, the speed is not a constant. Speed, as we have discussed before, the speed of the satellite depends on the distance. It's inversely proportional with the distance from the Earth. So when it is very close to the Earth, it rotates very fast. The speed increases. When it is very far from the Earth, the speed slows down. That's Kepler's second law states about. Okay. So here you can see satellite orbital velocity is not what? It's not a constant. Why it's not a constant? The satellites are moving faster when its location near the Earth, and it is slows down at its approach apogee. Apogee I will explain later. It is the farthest point on the orbit. We call it apogee. So when the speed is when the satellite is at farthest point, it slows down. When the satellite is very near to the Earth, it rotates with very fast speed. That is Kepler's second law states. Okay, so Kepler's third law is, in short, we put it like this. The square of the time period, t is a time period for a satellite to take one complete rotation around the Earth. How much time the satellite will take to make one complete loop rotation around the Earth? It is t, time period. So the time period square is proportional with the cube of the distance r from the Earth. Kepler states this in 16th century, but he don't know the reason why. But he analyzed it through experiment, repeated data analysis. He found out that the square of the period, how much time a satellite takes to complete one rotation, the square of that is proportional with the cube of the distance. So if you have Earth here, this is our Earth. We have a satellite here, which rotates around the Earth with a distance r1. Another satellite r2. Okay, so what does it mean by Kepler's third law? How much time it takes for this satellite to rotate around the Earth, one complete rotation? Let's say it takes t1 time. This satellite with a distance r2, it takes time t2. So always this t2 square, the time for this one divided by r2 square, it's proportional here. Okay, it is a constant always. T1 square divided by r1 square for this satellite. The ratio, this t is in square, r is in cube. R is in cube, right? The distance is in cube. Always the ratio is some constant k. Always. This is another way of expressing Kepler's third law. For example, if this satellite in geostationary satellite, if this geostationary satellite, the distance is at 6,000 kilometers. How much time it takes for one complete rotation? 24 hours. That is T. T will be 24 hours. Okay. If this satellite is LEO satellite, it takes only 8 hours to complete one rotation. But the ratio of time square divided by radius cube always is a constant K. That is very, very important law for satellite communication. We call it Kepler third law. Okay. Okay, let's continue discussion on orbital parameters, the third topic. So the first point we need to discuss is what you call it apogee. So as you know, satellites orbits from first law, from Kepler's first law. The orbit is elliptical. So elliptical means there are points where the satellite is very close to the Earth. And there are points which is the farthest point. I think this is the farthest point. When satellite is here, it is very far from the Earth. So what is apogee means? Apogee means it is the farthest point of the satellite from the Earth. It's defined as apogee. Okay. To the opposite that, it is perigee. The nearest point, the point which is closest to the Earth, is what we call it perigee. Okay, perigee and apogee. But apogee is the farthest point of the satellite from the Earth. So when you go back to our Kepler's first law, here we have orbit. The path of this satellite is elliptical. So the satellite will be at different points, right? It can be at different points. Now, where the satellite is very close to the Earth, maybe at this point. When satellites reach here, this distance is very near. That point is what we call it what? Perigee. It's called perigee. When the satellite positioned here, the distance is very far distance from the Earth. This point is called apogee. Okay, it's called apogee. So that are the first two parameters, orbital parameters we should know. Next, line of upsides. So what does it mean by lines of upsides? It is the line joining the 2 points, perigee and apogee, right? You know, apogee is the farthest point from the Earth. Perigee is the closest to the Earth. When satellite is closest to the Earth, we call it perigee. So if you draw a line to join if this is perigee and this is apogee, so if you draw a line to join these 2 points, what we call it the lines of upsides. So the line joining perigee and apogee to the center of the Earth is called line of upsides. Okay, next point, ascending node. How we define ascending node? The point where the orbit crosses the equatorial plane. So here you see this is Earth. Okay, the Earth is here. This is equatorial plane. This is our equatorial plane. This is the orbit. This is the orbit. The satellite is following this orbit. So what is the ascending node? As you can see here, ascending node is the contact point between the equatorial plane and the orbit when you go from south to north. when you go from south to north through the orbit, there is a contact point where the orbit and the equatorial plane meet. That's called ascending node. On the opposite, when you go from north to south direction like this, again, when satellite follows this path, there is a point here where the satellite and the equatorial plane meets. Point where the equatorial plane of the Earth and the orbit of the satellite meet at this point. That point is called descending node. So what points we have discussed? So parameters of, we discussed apogee, the farthest possible point of the satellite from the Earth. If it is a circle, if the orbit is a circle, the satellite will be always equal distance, right? Equal distance. So what will be the speed? If this is Earth, and if the path is a circular path, satellite follows, if it is circular path, orbit, what will happen? R is always constant, right? The distance of the satellite from the Earth is always constant. When R is constant, V also will be constant. The satellite will rotate at constant speed. Why? Because we said speed of the satellite is inversely proportional with the square root of R, right? So, but from Kepler's first law, we understand that the path followed by satellites is elliptical. Elliptical means R changes when satellite rotates, the distance changes, the speed changes. Okay, so the farthest point, we call it apogee. When satellite becomes very close to the Earth at some point, the closest point is called perigee. The line joining these 2 points is called line of Assayas. Okay, third parameter. Fourth parameter, we have equatorial plane, as you can see here. So when satellite goes from south to north, there is a crossing point at the equatorial plane. That point is called ascending node. When satellite rotates from north direction to south direction, as you can see here, again it contacts the equatorial plane of the Earth. That point is called descending node. Ascending node, descending node. Okay. Before we finish, I think Redwa, you have a question. Okay, I have a question here. Repeat Kepler first law. Okay, Kepler first law. Kepler first law states that if you have Earth